Hello, Chemistry 2330. We are going to continue with our chapters. This is chapter 10, part A, or part 1. We're going to talk about amines. And so that's a follow-on to our alcohols, where we had an oxygen attached to our carbon system, and now we have a nitrogen attached to our carbon system. So let's move on and talk about the structure and classification, okay? So the general structure of amines are the fact that we have a nitrogen attached to a carbon system here. Now, the simplest nitrogen compound we have is actually not organic. It's this one right here. This is ammonia, where it has three nitrogens attached to a, three hydrogens attached to a nitrogen, and that makes it the ammonia. And so we actually use ammonia as a solvent sometimes and as a starting material for a lot of products, but it technically isn't an amine because it does not have a carbon attached to it. So once we attach a single carbon to the system, we end up what we get calling a primary amine. If we attach two carbons to that nitrogen, it's a secondary amine. And if we have three carbons attached to the nitrogen, we call it a tertiary amine, okay? They can be alkyl groups or aryl groups. It doesn't matter as long as there's a carbon-nitrogen bond, okay? So again, ammonia is not a primary, secondary, or tertiary because it's not bonded to carbon, but once we bond it to carbon, we classify them as a primary for one, a secondary for two, and a tertiary for three bonds to carbon, okay? This is the opposite of halides and alcohols, where it's how many things are bonded to the carbon the halide or oxygen is bonded to. Here, it's all about how many carbons are attached to the nitrogen, okay? And I believe it's the only one we're going to talk about that breaks that rule. Okay, so if we look at them, they are also further classified into what we call aliphatic amines, which are where all of the nitrogens are bonded to alkyl groups, or we have aromatic amines. And we just learned about benzene in our last group here. So if we have a benzene attached to the nitrogen, that counts as an aromatic amine. We can also have one of the other heterocycles bonded to it, but that means that this is an amine. Here, if we have an aromatic group and an aliphatic group, that still classifies as an aromatic amine because we do have one aromatic group. Notice, but if we, instead of having the benzene attached, we have that benzylic, these is an aliphatic group, and this is an aliphatic group, and this is an aliphatic group. So that makes this an aliphatic amine. Even though there's an aromatic substituent close to it, the aromatic ring is not bonded directly to that nitrogen. Therefore, it is not an aromatic amine. Okay, so now that we have that done, let's talk about some of the heterocyclic amines we have. Okay, so we already talked about this in the last chapter, things like pyrrole and pyridine. These are called heterocyclic aromatic amines, and we used those before. And of course, it's important to note that, you know, we have nitrogen, and this one's tertiary because it's bonded to three carbons, and this one's a secondary because it's bonded to two. But they don't have to be aromatic. They can also be aliphatic amines. So if we don't have double bonds, and these are just the aliphatic rings right here, we can call them heterocyclic aliphatic amines. Okay, and so the rest, there's, if you can think about it, there are additional hydrogens bonded to all the system, and so that there are two hydrogens here, two hydrogens here, etc. And so they are aliphatic hydrocarbons. Okay, so what can we do with them? Well, let's talk about how we can have multiple things on the same system. So in the case of connonine right here, we have our cyclic aliphatic amine right here that still has a hydrogen on it. So we would call this a secondary heterocyclic aliphatic amine. Here we have actually both. Nicotine right here has a heterocyclic aromatic amine and a heterocyclic aliphatic amine, and this happens to be tertiary because it has three different carbon groups bonded to it. So we can have both types in the system here. Now, if we look at cocaine right here, we have a nitrogen right here. It's the only nitrogen in the system, and it's bonded to this aliphatic bicyclosystem here. So we have an aliphatic cyclic amine. Okay. So when we name them, what we're going to do is if it's an aliphatic amine, we can just take the longest carbon chain, like our normal our normal rules for nomenclature, and add the word amine at the end to signify where it is on the system. So, for example, in this first one we have here, we have 1, 2, 3, 4 carbons here. So that means it's butane. And if we number it on this side, we get 3, that's too high. If we number it on this side, we get 2. So we have 2 butamine. Butane, we drop the E and add amine to it right here, okay? So let's talk about this. Okay, if we were to name this right here, this would be our benzene ring, but we have an aliphatic chain on it and it's not a common name. So we have to name it as the phenyl substituent. So that means our longest aliphatic chain right here is these 2 carbons. So that gives us ethane right here. So that makes it ethanamine right here. And then we have to figure out what's our shortest numbering here. So it'd be 1 and 2, since those are our 2 there. Therefore, the amine is on the first carbon and the phenyl group is on the first carbon. If it's on the first carbon, just like with an alcohol, we don't have to specify where it is. So we have ethanamine is the compound we have, but we have the phenyl substituent on that 1 carbon too. So we have 1 phenyl substituent. And if we look at our priority here, we have a hydrogen back here. This takes our first priority because the nitrogen has a higher Z number. This takes our second priority for our chirality because of the, actually, let me do the chirality in a different color so that we can see it better. So if we're talking about just the chiral priority here, we have our nitrogen is 1 because the carbons, it's higher than carbon on the periodic table. This would be 2 because we have carbons bonded to multiple carbons. This would be 3 for the sake of the chirality priority. And this would be 4. So this is in the back and this is our hydrogen. So we have 1, 2, 3, which puts us counterclockwise, which gives us the S configuration, okay? So then if we have multiple amines on the same hydrocarbon chain, we just have to put where they are on the chain, and then we end up with our di, tri, and tetra that we would use for an alcohol or a halide. So in this case right here, we have the 1,6-hexane diamine. Okay. Now, when we talk about the aromatic amines, we have to look at their common name that they retain here. So in the case of the first aromatic amine we have is aniline, which we learned about in chapter 9. Right here, we start with that as our parent group right here, and then we have to signify where the substituent is. Here it's the nitro group, and so we go 1, 2, 3, 4. So that makes 4 nitroaniline, or that's the para substitution, which is what the P is. Okay, so in the case here, we have 2 competing ones. We have, this could be toluene or it could be aniline. And so aniline is the higher Z number, so we're going to make it the higher priority. So we're giving it the aniline designation. And then this methyl group is on the 4 position or the para position. It also has a common name, and the common name is toluidine. So it's kind of like a combination of the aniline and the toluene to be toluidine, okay? So in this case here, again, if we looked at the name, the aniline would take place over the oxygen here, and we would get a total of, with aniline, and then we'd have a substituent on here as the methoxy. Now, the reason that the methoxy is the substituent here is because ether ranks lower than the alkane or the aromatic carbon than the aromatic system itself. So we'll end up with aniline with the methoxy group, and it's in the 1, 2, 3 position. So that makes it 3-methoxy. It actually does have a common name, but don't worry about that. The UPAC name is actually much easier to remember. Okay, so if we have multiple functional groups here, then amine is typically lower priority. Okay, so in the case of an alcohol, alcohol takes priority, or the benzoic acid would take, the carboxylic acid would take priority. And so the amine group becomes a substituent. So when we have an amine group as a substituent, we call it the amino substituent, and then we name the rest of the parent. So in this case, we have two carbons. And since we're naming it for the alcohol, this is the 1 position, this is the 2 position. So we have ethanol as our parent, and then we have it on the amine group on the 2. So we have 2-amino ethanol. In this case here, we have benzoic, the carboxylic acid naming the benzene ring system. So that's our common name is benzoic acid, and it's in the 1,2 position. So it's 2-amino benzoic acid. Okay. There are also some common names for the very common aliphatic systems right here. So if we just have a methyl group on the aliphatic amine, we just call it methylamine right here. If we have this alkyl group here, and it happens to be the T-butyl group, we call that T-butylamine right here. And in this case, we have 2 different cyclopentane groups. So we have cyclopentyl right here as substituents, but we have 2 of them, so we call it di. So it's dicyclopentylamine. In the case here, we have 3 of the exact same groups right here, giving us our triethylamine. So in all of our common names, we would end with describing what the alkyl group is and then giving the word amine at the end. And the different alkyl groups are not necessarily the longest chain if you add them all together, but it's the groups that are attached to the nitrogen themselves. Okay, so that was if we had a neutral tri-substituted nitrogen. Okay, if we end up having to make a salt out of it or make it a quaternary material, that's where we have 4 things bonded to nitrogen right here. If we have 4 things bonded to nitrogen, that's going to take away 1 of its electrons and give it a total of a positive formal charge. And we call those ammonium salts. So in the case of this one right here, we have 1, 2, 3, 4 methyl groups attached to it. So that gives us tetramethyl. And then because it's a nitrogen with a positive charge on it, we call it ammonium. But then there has to be a counterbalancing charge. And in this case, we have chloride as our counterbalancing charge. So we name what the ion is here. So in this case here, we have an unsymmetrical one here. This group right here is pyridine right here. And then we have this long group right here. So we have 1, 2, 3, 4, that's 14, 15, 16 carbons. So we have hexadecyl as our substituent here. And then this group right here is pyridine. So we have to change it to our pyridine salt. So that makes pyridinium. And then we have our counterbalancing ion here, which is chloride. So it's hexadecyl pyridinium chloride. Now the common name for the hexadecyl group is called cetyl, and so occasionally you'll see it as cetyl pyridinium chloride. All right, so now let's look at this one. All right, this one is not an aromatic amine because we have this benzyl group now. This whole substituent right here, remember from our last chapter, chapter 9, is our benzyl substituent. So we have a total of 1, 2, 3 methyl groups here, plus the benzyl, right? And so benzyl comes before methyl alphabetically, so we put it first. So we have benzyl, and then we have to signify we have 3 methyl groups, and then so we have that. And then we have an ammonium because we have a positively charged nitrogen, and our counterbalancing ion is our hydroxide. So we have benzyl trimethyl ammonium hydroxide. Okay, so let's talk about some of the physical properties of amines. First of all, amines are polar compounds. Even if the ammonia itself is polar because we have a lone pair. So we have nitrogen, hydrogen, 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 and we have a lone pair on there. That's making it trigonal pyramidal with that lone pair up there, which makes it a polar compound. So these lone pair here, if you have that lone pair intact, you will have a polar compound. Okay, so let's start substituting it and looking at how the properties change by the substitution. If we have a primary or secondary amine, that means that they have at least one hydrogen left on the nitrogen. If it has one hydrogen left on that nitrogen, like methyl NH2, that means it has two nitrogens on there, or the dimethyl MnCH3H. Oops, that means we have right here. Okay, if we have a hydrogen available here, it will hydrogen bond. However, it's not as strong a hydrogen bonder as the OH because the electronegativity difference between the nitrogen and the hydrogen is only 0.9. That makes it a polar bond, but not a strong polar bond. And if between the oxygen and the hydrogen, that's actually 1.4. So this is a more polarized bond, therefore this hydrogen bonds more. So that means that alcohols and water affect their boiling point much higher because they bond more strongly, they hydrogen bond more strongly. So if we think about the boiling point of the methylamine right here, which is analogous to the methanol here, we actually don't see the significant gain in boiling point we get from the hydrogen bonding with the alcohol that we get with the amine. However, we do see a boost than if it didn't have those at all. Okay. Now, remember that if we looked at the hydrogen bonding on our thiols right here, the difference there is 0.4 degrees, and that doesn't do any hydrogen bonding at all. So our thiol doesn't hydrogen bond. Our amines hydrogen bond, but not as strongly as our alcohols hydrogen bond. So in looking at that series, we're thinking it's right in between the hydrogen bonding ability of thiols and the hydrogen bonding ability of alcohols. And that concludes section 1 of amines.